everyone. This is Group 19, and we are going to present our project, which we call FlowDB. So the popularity of NoSQL-based systems has been increasing tremendously to handle big data efficiently. Also, out of the 39.5% share which NoSQL has currently, about 63% of it is filled with MongoDB users. However, a lot of users are still more comfortable working with relational database architecture. Our application tries to bridge this gap by providing a GUI-based SQL-like environment for working with MongoDB. This helps in leveraging the advantage of distributed systems without worrying about its complex concepts and implementation. Our objective is to allow the users who are familiar with SQL to run their queries on a distributed system like MongoDB without knowing the internal functioning of the query. FlowDB is a flow-based pipeline for data ingestion as well as processing and analytics. Our pipeline works for any dataset in general, given its CSV file as an input. Users can design or define their schema, perform data cleansing steps such as handling null values and duplicates or enforcing data types. We also provide an interactive way for performing simple select and aggregation queries like ranges, min-max, and percentiles in a highly abstracted form. We're using MongoDB as our data store, React for our front end, and a local node server in the backend for querying the database. The data flows in JSON formats, which is easy to operate for MongoDB queries. And using React allows us to reuse the components and manage their state effectively. From now, Tejas will continue.
Yeah, so we faced a lot of challenges during the implementation of the project. Some of them are listed here. The first challenge that we faced was enforcing the data types for a schema. So we chose to typecast the values being inserted from the baseline collection at the time of creating the user-specified schema. The another challenge that we faced was how we would design the queries and which all queries we would allow the user to choose from. So we decided to keep the choice very limited so that it would be easier to handle these queries in the backend. So we decided to keep only simple aggregation and selection queries, and this can be extended in the future as well. We also, due to the lack of time, we haven't extensively unit tested each component. So that is also another challenge that we have faced because of the lack of time. We will work on this as a future aspect.
Hi, so I'll continue from where Tejas left off. So we did some benchmarking test just to see the performance of it. So the main dataset which we took is the Paris house pricing. So there's a very popular dataset like used for all ML assignments, and it consists of about 1 million rows. And to benchmark this, what we did is we wanted different sizes. So we randomly sampled and created sets called small, medium, and large with 100, 1,000, and 10,000 rows respectively. And the last one, which is the full, which consists of all the 1 lakh rows. So to show that our null feature works properly, we also had to create some null values, like synthetically put null values. So what we did is we took random 3 rows and random 3 columns and then replaced this original value with null. So this is what our data set setting is. So we ran 2 benchmark tests, one to highlight the ingestion and the other one on query processing. So what we did is our ingestion query consists of making 5 columns or like 5 attributes in the schema, and then we put different null replacement strategies, and we had 3 options: whether we do nothing about it, we drop the row, or we replace it with mean, and computed the performance time. And for the next set, what we did is we ran a query which was basically finding all the houses having square meters area greater than or equal to 100, and then finding the minimum size houses, the average of sizes, which is basically like the aggregate queries. Do note that if you want to show all the outputs on the output window, which we have and which you'll notice in the demo, it is going to be tough to make out what the output is. So we limited all the outputs till the 50th output. And also we have one query where it is the size greater than 75th percentile. Is basically like the quartile statistic, which actually like a lot of outlier detection algorithms use. So the time, one note is that the time is computed here in milliseconds, and it's computed from the time where we click the submit button, the request is sent, the data processing happens in the server, and the response is received. So it consists of the real-time performance of how a client would feel when they're using the application, and not only the database retrieval or the query processing time. So this is where the interesting starts. Like the one thing to note positive about here is that when the dataset grows in size, the time is growing. However, we have noticed one thing is that as you're using the same schema or the same data more and more, the time is reducing. And when we researched a bit, we found out that MongoDB actually caches in some of the frequently used aggregate queries and tries to speed up. So what we had to do is most of the times we had to flush the entire data store from our backend and rerun these queries to get the actual times. Welcome to the demo of the app. So we are going to select a dataset file first. So for that, I'll use the Paris house in the entire dataset of 1 lakh rows itself. So when I click submit, if it is successfully processed in the terminal here, will tell me what kind of columns which are already existing in the CSV file itself. So that I have some idea while designing the schema. It's like similar to what we try to do in pandas, like when we try to check the head of a CSV file, just to know what kind of columns and what kind of data we have. So to make a schema of my own, I need to use add collection. So there I'll have an option to have a column name, refer from, data type, and some controls. So I'll try to take square meters, and I'm going to say area of room. And data type I can constrain to double, let us say, and then I can do a null check. So either I can drop them, I can replace them with something, or retain them. So let's go with replacement. And here I can actually write mean. That means it's going to replace with whatever the mean of that column is. So this is a pretty common imputation technique which we do in data processing and pre-processing steps. So once this is done, I can add more rows also. So suppose I want number of rooms, let's consider is new build, new house. So I'll make it Boolean. That's fine. And I can add one more. Let us see. Has storm protector. So storm protected. Let's name that. And data type is something was Boolean. Fine. So once it's done, I click on finalize collection. So I can create more such schemas. So once you can create, like, you can, the same thing is going to appear by using add collection. And after this is done, to pass them all together to the backend, you're going to use a finalize schema. So I'll click on finalize schema to do it. Yes. So now the submission is done, and we are on to the next screen for the query. So that was the part involving the data ingestion. So now we have the query processing part of it, and we are trying to implement similar interactive approaches here also. So I suppose I have a select query option. So I have the table names. The table names here will be auto-generated. So we are planning, like in a future work, we can give control to the user itself to decide on what kind of a table name they want. So here it's auto-generated. So it's a schema 2. And if I want to, like, take any of the columns of the schema which I created, so area of room, right? So I can check a condition here. So I'll check whether the area of room is greater than some value, let's say 15. And I have to limit the output so that the terminal does not get clogged up. So I'll limit it to 50. So once I'm done, I'm going to just submit the query. So it's going to say that the query was successful. So now I'm going to see the output in the terminal. So this is the output. So it's informed the document format in which, like, MongoDB stored. So here also I want to like to highlight a future possibility that we could make it look better and give a proper tabular kind of output similar to how MySQL does it. So I'll try to show an aggregation query also. So I have a schema name, and then let me take an option of what area of room or a new house. Let us take area of room itself, and I would try to find out the maximum. So I'll do this, and I click on submit. The output is ready. I click on show output in terminal. So if I scroll down the terminal, I can see the maximum area is 99999.
So that was a quick demo to see how the program works. But now Tejas is going to do a much detailed demo showing how the program works in the backend.
So let's begin the demo with uploading an Paris housing dataset. So this is a dataset that the user would upload to the system first. Yeah, as you can see, the system has detected these columns from it. Let us say that we choose a collection whose name is, let's say, column names is, let's say, square meters. Taking from this. Here, we want to show how it is being run in the backend. So let us choose a null check, and let us replace the nulls with a mean value. So this would help us understand what is exactly happening when we run this query in the backend. So let us finalize the collection, and let us also finalize the schema. Yeah, we need to wait for the backend to run. Right. So as you can see, we have a OK done message, which means that the query has successfully run in the backend. So let us also let us also use Mongo Compass to check if it has actually run in the backend. So as you can see here, we can't really find any key which is null. So we could also search over here. Let us go to the schema and analyze schema. Yeah, here as you can see, there is no, over here we can't see any null value present. Therefore, the query is working. So let us see how it is actually being run in the backend. So when we call the build schema, when we send the schema to the backend, it is initially sent to this function over here, and that calls a build collection function, which is used to insert the data into the schema. Upon inserting, which is a normal procedure of just taking values from the baseline and uploading it to the collection. After doing this, we call a run constraint function. This function is used to perform the checks that we would perform given by the user. So here, in this case, we are talking about the replacing null values with mean. So let us go through that. So as you can see here, this is the run constraint function, and we go through each column in the schema, and we look for the constraints that is provided by the user for that particular column. So in this case, we have a null check value to be 1, and we want to replace that null value with a mean value. So this is the function where it is. This is the function. This is the part of the code where the flow is going to be directed to. So here, what we do is we first run an aggregate query, which is given by this, to find out the mean value of the particular column. So this is where we are finding the average value of the column, and we are just projecting that value as average value. Now we take that average value and we update that to all the columns in the all the rows in the all the documents in the collection which have a null value. So in this case, that is run by an update many query. So this is that part where it is being updated. So we have an update many query where we set the column name, which is null, to be the average value. So this is how the average value is being changed. If we want to see what exactly is also happening, we can see here, we have console logged the average result, and we get the average value over here. This is the average value, and all those null values are going to be replaced with that. Now let us move on and add a select query. So let us choose this, and let us say greater than, let's say 40, and limit, let's put 10. So this is a selection query, and we will see what kind of an output is given in the terminal. Yeah, the output is ready, and let us go back here. And yeah, as you can see, this is the query that is being run, and these are the outputs which is coming from it. There's clearly a lot of outputs which are coming from it, as seen over here. So yeah, let me go through the backend code which explains what is happening. So yeah, we ran a selection query. So in a selection query, we first, that selection query is being routed to this function over here, which is this function over here, which calls the select query. It basically checks whether it's a select query or a aggregation query, and calls the select query function or an aggregation query function. So here is a select query, so it calls the select query function. So when it goes there, there is a switch statement which checks which condition it needs to carry out. And then based on the condition, we have a corresponding query. So in this case, because it's greater than, we have a simple query which checks the column name value to be greater than the RHS value. And then we call a find query with a limit given by the user. And that limit is, that result is given back and passed to the front end. So that is what happens here. Now let us run another aggregation query just for the completion's sake. Let's take maths and let's submit the query. Here again, the maximum value that we can see here is 99,999. This is again handled in a similar way. As we had a select query function, we have a aggregate query function which is used to handle aggregate queries. It also has a switch statement which has a case max. In this case, it runs the appropriate query. It basically sorts all documents in the collection in the descending order, and limit 1 takes the top value. This is then stored in the result, which is sent back to the front end. If you want to confirm it again, we could see here that the max value of the whole collection given by this line over here is 99999, which is the value which is being outputted here. So that's how the queries in the front end is being handled in the back end and run on MongoDB.
So lastly, we are in the conclusion part of our presentation after all the video demo and the explanation of what's going on behind the hood. So yeah, yes, the first lesson which we have learned is that yes, it is indeed possible to have a best of both worlds scenario and create a system which allows someone to perform data ingestion in a SQL way, where how they're familiar with writing DDL scripts in SQL, but leverage also the benefits which MongoDB brings in as a NoSQL system. And the novelty of our approach to point out is that whatever we have created is dataset independent. So you can actually pass any of the datasets which you have. It might be as raw as possible. And since there is an inherent column ordering there, so you can retrieve those columns and create your own arrangement of tables and schemas. And this actually helps in places where people do not have much idea about NoSQL, or maybe they just have idea about SQL or Tally in business especially. So the technological literacy aspect, the gap can be bridged with the help of our solution, especially when for people working as data entry professionals in finance or in medical sciences. Also, the thing is, when we were coding the system itself, we realized that this can never replace the traditional scripting method which we have learned in the course so far, and that will always have some benefits and will be superior than the previous one. And also, if you want to extend this design itself, right, the design methodology. So when we are going to write complex queries, when you're nesting, when suppose you have a select from an aggregate query, and then there's a query inside the query, when you nest them, you have different outputs taking in as different inputs, then it's very tough to represent it in a UI fashion such that people can do it using by simple mouse clicks and clicking on buttons. But still, we feel that this is a direction the project can take in the future. So we have only included some minor data types, which are pretty common. So we can add more constrained data types. We are also thinking about adding the notion of references. So basically foreign keys in what we define in SQL, and also the changing the ID. So for now, Mongo is giving its own ID. So there has to be some way where we can be able to declare the other key as the primary key or something. Also, we can create a better output UI. So for now, we're just taking in whatever MongoDB returns the document output, and we're not doing anything more. So we can create a tabular kind of an output, which MySQL returns. And we did not discuss much about joins because our main focus here in the project was the data ingestion pipeline rather than the processing pipeline. But we feel that a processing pipeline is also possible, and it holds a higher potential to make this application better. And last but not the least, we called it FlowDB, but we haven't been able to implement the drag and drop features and the attachment, the interactivity which comes with having something like Flow. So it's similar to what the MIT Scratch tries to do in coding. So if we can implement that, then we can say that it really brings the flow in FlowDB. So that's it from our side. Thank you.